Hello everyone, and welcome to some more remote learning. Today, we're going to continue with that concept of slicing solids to find the volume, except this time, now we're going to find the volume of solids of revolution. So that's the case where we're going to take some area, but we're revolving it around either an axis or a line, and then finding the volume based on that. And in this video alone, I'll be just revolving around either the x-axis or the y-axis. And in the next example and practice sheet, we'll be revolving around something other than the x-axis and the y-axis. But just a heads up, it's all based on that radius. And our radius is always the distance from the line we're revolving around. So just keep that in mind as we're working through this worksheet. So the first method we're going to go over is called the disk method. So let's take a look back at an example from the previous worksheet. I believe that was example 1, where we found the volume by using the general slice method, and we used squares. This time we're going to find the volume, but we're going to revolve it around the x-axis. So if you can think of taking this figure and revolving it around this x-axis, we're going to have something. I'll just do a rough sketch real quick. Here is the y-axis. I'm going to draw the x-axis at an angle, so that you can envision us taking this function, which, remember from that previous worksheet, was the square root of x. So here's the square root of x, and then we have some line. This was that x was equal to 4. So here's our x equals 4 line. Now think about revolving that around. We're going to have circles. So that's going to be almost like a bowl or a vase coming at us, if you can envision that. And it's a little hard to draw in 3 dimensions. I'm not the best artist, but if you can envision that figure being formed. Let's look at it from a different angle. If I was to physically take one of these circles, so let's get rid of those 2 big ones. If I was to take this first circle here, so if you go to this, let's put this disk at about right here, because we know that the square root of 1 is 1. So I'll put this disk right here, and I'm going to draw it like a rectangle. So this would be half of our disk, right? Because we're revolving it all the way around. So this would continue down here. So if that's half of our circle, remember what I said in the start of the video? We care about our radius, which our radius is going to be this distance here. So the distance from the axis of revolution to our function, which in this case, that height is the square root of x. Over here, what's that height? That radius is the square root of x. It's whatever that y value is. So now that we have that radius, we know how to find the area. The area of a full circle is pi r squared. So let's go ahead and build this volume using that information. So the volume is going to be equal to the integral from a to b. So from our starting value to our end value, here we're starting at 0 and ending at 4 in the x. Hence where I start drawing those rectangles and where I stop drawing those rectangles. So that's from a to b. And then we need pi r squared, but r, our radius, is a function of x. So that r is going to be f of x. So we're going to have pi f of x squared. There's our pi r squared. And then we're going to integrate that with respect to x. So you can envision our dx being the width of those rectangles. So multiplying by another length, if we take the area and multiply that by another length, that's going to build our volume. So again, we need to remember that f of x is our radius. And I'll just make a note of that in that little box. So in example 1, it says, let's continue solving what we started. It says, let R be the region bounded by y equals the square root of x, y equals 0, and x equals 4. Hence, this figure that we already have. This figure that's in that first quadrant, here's the square root of x is the red line, x equals 4 is the blue line. We're going to use the disk method to find the volume of the solid generated, and I've got a typo, but I'll fix that before I hand out the worksheet to you guys. This is generated when r is revolved about that x-axis. So you can see we've already pretty much set it up. Our volume, V, is going to be from, well, our starting point was 0 in the X, where we started drawing those rectangles, and we finished drawing them at 4. And then, of course, we have pi, because that's some constant. Our radius is the distance from our axis of revolution to our function. So that distance is just the square root of x, because that's our function. So this would be the square root of x squared. So here's our pi r squared dx. So simplifying this down, we're going to go from 0 to 4. Pi, the square root of x squared, is simply x dx. So what I'm going to do is I'm going to integrate x, since pi is just a constant. So this is going to give me pi x squared over 2 from 0 to 4. I'll go ahead and plug in 4. So that's going to give me pi. 4 squared is 16, so pi times 16 over 2. And then when I plug in 0, that's 0. So all I'll have is 16 over 2 pi, which is 8 pi. 8 pi is my solution in example 1. Let's move on to example 2. In example 2, it says let R be the region in the first quadrant bounded by y equals x squared, which is that red function, and y equals 3, that blue function. So I'll go ahead and label those now. Here we have y equals x squared, and here we have y equals 3. We're going to use the disk method to find the volume of the solid generated when R is revolved about the y-axis. So this time we're going to be revolving about that y-axis. So we're going to be revolving around here. Now remember, we're using the disk method. So when we draw those rectangles, we want to be forming disks. So if you look back up at this first example we did, when we drew the rectangles vertically, when we revolved those around, we got a small flat disk. If you can envision taking a pen, and that's your rectangle that we drew, and the axis we revolve it around, you can see that's going to be a flat disk when formed. If, however, we were to draw our rectangles the other way with respect to y, if you can see that yellow box I just drew, if we took our rectangles and drew them like that and revolved them around the x-axis, we would not get a flat disk. We would get a shell, a cylinder essentially, which is not a disk. That is the shell method, which we'll do examples on that in a later example video. But for now, let's scroll back down to the example we're working on. So if I want a disk, if I were to draw my rectangles vertically, like up above, with respect to x, think about revolving those around the y-axis. That's going to give us a cylinder. We want to revolve and get a disk. So we're going to draw our rectangles with respect to y. So this is going to be integrated with respect to y. So if I was to fill this with rectangles, obviously I'll skip a few because that'll be really tedious to draw all those rectangles out. You can see that I'm going to be integrating with respect to y. The same concept still applies though. If I'm integrating with respect to y, my bounds are where I start drawing those rectangles and where I stop drawing those rectangles, going from the lowest value to the highest value. So you can see from my picture that I start drawing those rectangles at, well, again, if we're integrating with respect to y, we want things in terms of y. So I want the y value of where I start drawing those rectangles. So I start drawing those rectangles at y equals 0, and I continue drawing those rectangles up until y equals 3. So my bounds of this integral are from 0 to 3. Now if we're revolving this around the y-axis, we still are going to have the same kind of area for the disks. Our area of a disk is based off the area of a circle, pi r squared. So we're going to have pi. We just need to figure out what r squared is, but remember, we're integrating with respect to y. So our radius in this case if we're looking at it, remember I said that the radius is always the distance from the axis of revolution to that end of the rectangle, so essentially our function. But if we're looking at this, we're going from our axis of revolution, which is our y-axis, to our function. But what is this value? What is this length? But when we integrate, we don't want that in terms of x, we want it in terms of y. So what we're going to do is solve for x and plug that function in for our radius. So y equals x squared, that's really going to be that x equals the square root of y. And since we're only working in that first quadrant, as stated in our problem, we're only dealing with that positive square root of y. So I'm just going to replace our radius with the square root of y. And let's quickly think about this one more time. When we're revolving that rectangle around, we're going to get a flat disk. So you can see, I'll take this rectangle down here. We're going to revolve it all the way around like so. But this, pictured from a sideways look, is going to be a circle, where this dot in the middle would essentially be our axis, and that's out to our function, and we're taking that and revolving it all the way around. That is our radius, which in this case is the square root of y. Because I'm plugging in those y values, my distance is actually whatever x is at that point. And that's all based on my y values. Hence, we wrote x as a function of y. So before we solve this out, let's go back up to our box and write the formula for the disk method, but this time we're going to do it about the y-axis. So we know that volume is going to be equal to, as opposed to going from A to B, let's leave that as some x values, let's go from C to D. And then we're still going to do our pi r squared, except it's going to be pi r squared with respect to y. So since I'm doing pi r squared with respect to y, as opposed to having some function of x squared, I'm going to have some function, let's call it p, of y. We're going to have that function squared. But this is still the radius. Everything now is just in terms of y. So let's finish solving this out. We're going to integrate this from 0 to 3. We'll have pi, the square root of y squared is y dy. Integrating y will give me pi y squared over 2 going from 0 to 3. So plugging 3 in, I'm going to get 9 for y squared, because 3 squared is 9, and that's 9 pi over 2. And then I'm subtracting, plugging in 0. 0 squared over 2 is 0. So 9 pi over 2 minus 0 is obviously 9 pi over 2. That's our volume when we take the region in the first quadrant bounded by y equals x squared and y equals 3 and revolve it around the y-axis. Now, moving on to the next page, we're going to jump into the washer method, which I think the washer method is almost like an extension of the disk method, or you can think of the disk method as the simplified version of the washer method. So if we think about this region, which I drew here, bounded by some graphs f and g on some interval from a to b, if r is revolved around the x-axis, we have that solid of revolution. So this function that I have pictured below is the square root of 4x, or you can think of it as 2 root x. And let's go ahead and stop this region at x equals 4. So I'll go ahead and draw a line at x equals 4. Now, if you can think about revolving this around the x-axis as is, which way are we going to draw our rectangles if we're using the disk method? Well, remember, we want those flat disks. So if we revolved drawing our rectangles with respect to y, we're going to have a cylinder, whereas we want those rectangles drawn with respect to x, because that's going to give us our flat circular disk. So I'm going to be drawing my rectangles like so. However, let's say as opposed to having that function and then our rectangle going all the way down to our axis of revolution, let's have some other function so that our region, as opposed to being this entire region here, our region is now going to be bounded between two different functions. So let's go ahead and do some function. Let's make it y equals 2. So this purple line here is going to be y equals 2. So I'm going to take this region and revolve that around the x-axis. But if you think about taking this region and revolving it around the x-axis, let's go ahead and draw a rectangle really quickly. If I take that small rectangle, I'm no longer touching that axis of revolution, so I'm not going to have a solid figure. What's going to happen is if I'm revolving around some axis of revolution, I'm going to have a gap or a hole. So when I revolve that small rectangle around, it's going to look something like this, where I have this hole in the middle. So this is my region when it gets revolved around into a solid. Hence, it's no longer a disk, but a washer. But if we're looking at this, you can think of a washer as two separate disks, except we're taking out that inner disk. So we're still going to be using that pi r squared formula, the area for a circle, except now we're going to have one area and we're going to be taking away that inner area. So I'll put a dot in the middle here. This is like our axis of revolution. Let's calculate the area of this disk, because remember, integrating that area is going to give us a volume. So what I want to do is find that area of that shaded yellow region, which is going to be that outer disk subtracting that smaller disk. So if you can envision from here all the way out to that outer edge, that's like going from our axis of revolution all the way out to our outer function. So if we found the area of that full figure, that's going to be pi r squared. But I'm going to label this as pi r sub o for our outer. So that's our outer radius squared, would go from our axis to our function, which in this case our function is 2 square root of x. What's going to happen though is I'm going to subtract this inner area. So I'm going to quickly shade in that inner area, and I'll shade it in as blue. So this inner area, you could see, would be me subtracting if I was to revolve just up to that y equals 2 line around. So y equals 2 is our other function. So then I'm going to have from my axis of revolution to that inner radius, which the inner radius in this case, you can see, would be from the axis to the line y equals 2. So that's going to be pi times my r sub, I'm going to put this as r sub I for my inner radius, my r sub I squared. So that's me taking that outer area, that full area, and subtracting that smaller area. But remember, to get volume, we're going to have to integrate that. So before we jump into the basic formula, let's quickly reiterate. Our outer area goes from our axis of revolution to the top of our rectangle, that furthest distance away. So you can see here's that top of the rectangle going all the way to that axis of revolution is my outer radius, where the inner radius is going to be that smaller radius going from the bottom side of my rectangle, or the closest side of my rectangle, all the way to that axis of revolution again. So that's another way to think of it in terms of drawing a rectangle. That's why I think drawing those out, visualizing this is so important to really understand what's happening. Now, let's go ahead and actually write this washer method out in terms of functions. So again, we're going to have that the volume equals the integral of some area, and if we're revolving around the x-axis, to draw those disks or those washers, we're going to need to do it with respect to x. So I'm going to go from some value a to b, and I'm going to have pi times my outer radius squared minus my inner radius squared. So my outer radius, I'm going to say, is f of x squared, and my inner radius is, I'm going to say, g of x, and then I'm going to square that radius. and this gets iterated with respect to x. So again, my f of x is my outer radius, and my g of x is my inner radius. Now this might look a little different from what I wrote up here, but all I did is I took this pi and pulled it out of each of my terms. So I still have pi times r outer squared minus r inner squared. All I did was pull pi out in front. So here is my area that I wish to integrate with respect to x. That little width is going to help me build up my volume. So let's go ahead and continue solving the example above, but before we move on, we really need to figure out what a and what b are. And a and b, remember, if we're integrating this with respect to x, are going to be x values. And those x values correlate to where we start drawing the rectangles and where we stop drawing the rectangles. So looking at our picture, you can see we start drawing these rectangles at this intersection point here, and we stop drawing those rectangles when we get to x equals 4. So we know our upper bound is x equals 4, but what is our lower bound? That's when our functions intersect. So let's go ahead and write this all out. So using the washer method, revolving it around the x-axis, let's fill in those blanks. So our volume is going to be from our starting value, where we start drawing those rectangles, to our end value. We know our end value in terms of x is 4, but let's solve for that intersection point. That's when you can see our line y equals 2 intersects with y equals the square root of 4x. So this is when 2 equals the square root of 4x, which simplified is when 2 equals 2 root x. Dividing both sides by 2, that's when 1 equals the square root of x, which occurs at a positive 1. So that's when x equals 1. So this intersection point here is 1, and if we wanted to solve for y, although it's not necessary, that would be 1, 2, which holds true for both equations. If we plugged 1 in for x, we get square root of 4, which is 2, and there is no x, so that's always 2. So now that we have that intersection point, we know that we start drawing those rectangles at 1 and stop at 4. So our lower bound is 1 and our upper bound is 4. Now we're going to have pi times our outer radius squared minus our inner radius squared. So let's focus first on that pi r squared, getting that full area, and then we'll subtract that smaller area we don't want, which we already talked about this outer radius up above. Remember that outer radius is the largest distance from our axis to our rectangle, which is from our axis to the function y equals square root of 4x, because remember that was our outer radius. That's going to give us that full solid. So we're going to do pi times the square root of 4x, because that's that function, squared. Now we're going to subtract another area. We're subtracting another pi r squared, and it's the one that we don't want included in that solid. So that's that inner radius. So the distance from our axis to the bottom, or that closest point of our rectangle. That's what we don't want. That's what's getting subtracted out. That area that I had shaded in blue when looking at our washer. And that was from our axis to y equals 2. So our radius is 2, so that's going to be a 2 squared, and this is all with respect to x. Simplifying this, we're going from 1 to 4, and we're integrating pi times the square root of 4x squared is 4x, minus 2 squared is minus a 4, and this is all with respect to x. So integrating each of those terms, I'm going to have pi times 2x squared minus 4x. Integrating 4x, I get 2x squared. Integrating 4, I get 4x. And this is from 1 to 4. So I have pi times, I'm going to plug 4 in for x. 2 times 4 squared is 2 times 16, which is 32. And I'm subtracting 4 times 4, which is a 16. And then I'm going to be subtracting, plugging in a 1. But remember, pi gets multiplied to everything, so I'm going to pull that pi out in front. So putting an outer bracket on, keeping my pi outside of that, plugging in 1, I get 2 times 1, which is 2, minus plugging in 1, I get 4. Simplifying this down, I'll get pi times 32 minus 16 is 16, and I'm going to be subtracting 2 minus 4, which is a negative 2, so that's going to be 16 plus 2, which is going to give me 18 pi. So my solution in example 3 is 18 pi for the volume bounded by the region y equals root 4x, y equals 2, and x equals 4, generated when revolved around the x-axis. So 18 pi is my solution in example 3. Let's finish up doing example 4. So in example 4, we're going to let R be the region bounded by y equals x squared, which is this blue function pictured, and y equals 2x. So if that's our region R, I'll go ahead and shade this in yellow. We're going to be revolving that using the washer method around the y-axis. So we're going around this axis now. And remember, when we're using the disc and washer method, we don't want to get a cylinder when we revolve something around a shell. We don't want that. That's something that we'll get into in a later example video. What we want is something flat. Like think about a pancake, a disc, or a washer. So with that being said, how are we going to integrate this? Are we going to integrate it with respect to x, or are we going to integrate it with respect to y, how we draw our rectangles? If we integrate with respect to x, those rectangles will be drawn vertically. And if those rectangles are drawn vertically, think about rotating that around. We're going to get an actual shell, a cylinder. So we don't want to use this if we're told to use the washer method. If we're using the washer method, we're going to want our rectangles to be drawn horizontally, so that when we revolve them around, we'll get that flat disc or washer. So that means, with this case, we're going to be integrating with respect to y. So our volume is going to equal the bounds. Remember, that's where we start drawing a rectangle and where we stop drawing a rectangle. So where we'll start drawing our rectangles, that lower bound is at 0. And where we stop drawing those rectangles, filling this region in, is at this intersection point. So at that intersection point, we have to figure out not the x value, but the y value. So our lower bound is 0 in the y. Our upper bound is going to be what? Well, when does x squared equal 2x? So x squared equals 2x. Well, we can divide both sides by x if we feel like it, and then we'll get that x is equal to 2. So we stop drawing our rectangles at 2 in the x, but I want to know what we stop drawing our rectangles at in the y. So what I'll do is I'll plug 2 in to either equation, either 2x or x squared. Plugging it into either one, we're going to get 4. So our rectangles are stopped at 4. Those are our bounds of our integral. Now we'll do pi, and we have our outer radius squared minus our inner radius squared. Because pi, our outer squared, is that larger area, and we're subtracting that smaller area to get the area of the washer that we want. So if we can envision our washer, our outer radius goes from the axis of revolution. It's that distance, that furthest distance to the edge of the rectangle. So that's going to be to that blue function, which our blue function is x squared. Y equals x squared. So we're going out to that function. However, remember, we're integrating this with respect to y. So we don't want to throw in an x squared into our formula. We want to use the fact that x is equal to the positive square root of y, because we're on the positive side of that axis. So if this was the region that I have filled in, our outer radius is the square root of y. So our outer radius is the square root of y. squared. Now we're going to subtract that inner radius, which if we look at that, the inner radius goes from the axis of revolution. It's that shortest distance to our rectangle. So the inner radius is to the function y equals 2x. But y equals 2x is in terms of x. To put it in terms of y, that's going to be x equals y over 2. So that is our inner radius from the axis to our inner function is y over 2. So our inner radius squared, y over 2, that quantity squared. And this is all integrated with respect to y. So you can see if we were to distribute pi through, we'd have pi r squared. That's that largest disk, and we're subtracting pi r squared, that inner disk. So quickly, before we solve this out, let's go up and write the general formula. So the washer method, now we're going to say about the y-axis. That's going to be that the volume equals, now as opposed to using a to b, we'll think of that as the x values of the coordinates. We're going to go from c to d, the y value of those bounds. And this is going to be pi times our outer radius, which we want in terms of y. So this is going to be some function p of y squared minus, we want another function in terms of y, that's our inner radius, so that's going to be q of y squared. And this is all with respect to y. So p of y is our r sub o, or our outer radius, and q of y is our r sub I, that inner radius. However you want to label those is fine, just make sure they're in terms of y when we're integrating with respect to y, and in terms of x when we're integrating with respect to x. But overall, it's pi times the quantity, our outer radius squared, minus the inner radius squared. So let's finish this problem out, actually integrating. Simplifying, we'll go from 0 to 4, pi times the square root of y squared is y, minus y over 2 squared is going to be y squared over 4. So when I go to integrate this, I'll have pi times y squared over 2 minus y cubed over 12, and that's from 0 to 4. Y becomes y squared over 2 when integrated, and y squared over 4 becomes y cubed over 3 times 1/4, which is y cubed over 12. So plugging in 4, I'll get pi times 4 squared is 16, so that's 16 over 2, minus 4 cubed is 64, and that's all over 12. And when I plug in 0, I'll get 0 for that term, so I don't have anything to subtract. So pi times 16 over 2 simplifies down to 8, minus 64 over 12 simplifies down to 16 thirds. Because both 64 and 12 are divisible by 4, so finding a common denominator would be 24 thirds minus 16 thirds, and that was taking 8 and writing it as thirds, so that is 24 thirds, and 24 thirds minus 16 thirds is going to leave us with 8 thirds, and that's all multiplied by pi. So 8 pi over 3 is our solution in example 4. Now the big takeaway again is that the radius is that distance from the axis of revolution to our function, and our outer radius and inner radius depend on the axis we're revolving around and that further and closer distance. So I want you to take this with you, this concept, into the next video, because in the next example video, I'm not going to be rotating around an axis, I'm going to be rotating around a line. So in the next video, we're going to be adding or subtracting constants to help us get that actual radius. So stay tuned, continue on, and if you have any questions, let me know. But until next time, good luck with your online learning.